Today's topic, eccentrically loaded bolted joints. Let's go. Okay, so for the purposes of this exam, we're going to take a look at a bolted joint that's going to look something like this. Probably all of our problems are going to have some type of diagram that looks like this. So in order to solve these within 6 minutes, our problems are probably going to be set up a fairly straightforward way. We're going to say that they fail in shear, but what we mean by that is shear stress is the dominant stress in these problems. We're going to be looking at the induced shear stress and either just solving for it or maybe comparing it to the bolt allowable shear stress or something like that, but this is the key point here. We're going to be finding shear stress in our fasteners. And we're going to go ahead and neglect friction because we're typically not given any information about this interface here. We're not given a mu value or anything like that. That's why I say we're solving for shear. If we have a problem set up like this, that's a good thing for us because we're going to use the critical fastener theory for solving this type problem. And all that really says is that there is a fastener or fasteners that are very similar that are going to govern the acceptability of the joint. So we're going to find a bolt that is the most highly stressed, and that bolt is going to limit or govern the design of a joint. We're going to be finding the maximum resultant stress in that bolt, and we're going to find that by taking the vector sum of our primary and secondary shear stresses. Or another way to just make this faster, the critical fastener is the one that's farthest from the bolt group centroid. We'll see why, but you know you can find something that's far from the centroid, you got the problem solved. Or at least you got the bolt identified. Okay, so this is the formula we're going to be using to solve our problem here. Pretty straightforward when you look at it. Our resultant shear stress is equal to the vector sum of primary and secondary shear stresses. And we are going to go over those in just a moment. But this is really the only formula. Now, we're going to go over its components, but this is it. And imagine I've got, we'll just start right here and we'll go back to our previous example. Imagine I've got 4 bolts. And I've got a load coming off of here. Call it either V or F, either one, doesn't matter. What is our primary shear stress? So that's simple. Primary shear stress is just the general shear stress formula, V over A. And as we take a look, how does it apply to a bolt group? We're going to say, and this is one of the key assumptions of how these problems are going to be set up, that our primary shear stress is V over A, but divided equally between the number of bolts. In this case, n equals 4. And I've used V here as an annotation simply because V over A is the way general shear stress is written. Now, a couple assumptions, though, that these resultant forces or stresses act in the same direction as the applied force. So if we've got a V of 16 pounds force, we're going to divide. This is what each bolt sees as a component. And it's going to be equal to 4, so on and so forth. Get it? Okay, shared equally between bolts and acts in the direction of V. This is the simplest part of the problem. Very easy to solve and very quick to solve. Secondary shear stress, we're going to treat that, well, not treat it, it is the torsional component. And our general formula for torsional shear stress is TR over J. Now you're asking, what's T? What's our torque? Okay, going back to our example here, our torque is F times E, eccentricity. Our eccentricity is the measure of our bolt group centroid to the load. So that's our torque. Our torque is V or F times E. And you're going to be asking next, okay, what's our R component? Good question. I'm going to redraw this here so you have a little more space. Bulk group centroid. What is our R value in our R term? Well, we've got a torque twisting like this. This is what the resultant, or excuse me, these act at right angles. This is what the stress vectors will look like for secondary shear, and they act in the direction of rotation. This value here, the radius from the bulk group centroid to the fastener under investigation, is our RI term. If the bulk group is symmetric, all our RI terms are equal. So this is the radius to the fastener under investigation. Investigated. And what's our J term? Yes, it's a polar moment of inertia, but what is it in this regard? It's the torsional resistance of the bolt group. Not the bolts themselves, we'll see that in a moment. It's of the bolt group. And the key assumption here is it acts in the direction of rotation. Notice too that all these vectors act perpendicularly to the radius. Okay, let's investigate the polar moment of inertia, because it's a lot more complicated. So our polar moment of inertia is for the bolt group, torsional resistance of the bolt group, and it's made up of several terms. If I have a bolt group here, and it has a centroid, I have a J value for the centroid. Well, we don't have any geometry here. There's nothing here. So there's no resistance to turning at the centroid because there is no geometry there to do any resisting. So that leaves us with, okay, how do the individual fasteners contribute to the torsional resistance? And here we have to use our parallel axis theorem. So let's go investigate fastener 1. Let's call this fastener 1, so on and so forth. Let's break this down a little bit. What is this value? Polar moment of inertia for the bolt, number 1, comes out of the manual, comes out of the reference manual. We can look up a J value for a circle. It's pi r to the 4th over 2. And the r here is the radius of the bolt. Now, curious here, this goes to 0, too, because bolts don't have resistance to turning inside of their holes. That's the purpose of a bolt. So that leaves us only with the R1 squared A1 term. R1, and we're going to have an A1, and also has a J1, but we've seen that that goes to 0. And we're going to write a term for every fastener in the bolt group. So on, and you're going to end up with a doozy of a term like this. All right. The summation of 1 to the number of bolts of the radius to each individual bolt times its area. That's a big term, and we've taken a long time getting there. You can see here, there's our radiuses, radii. But let's do a couple of assumptions here and see if we can reduce this a little bit. If our bolt group is symmetric, all the R terms are equal. And we're assuming also that all the fasteners are the same diameter, so all their areas are equal. So let's rewrite this term. Sum from 1 to n, Ri squared AI now becomes the number of fasteners times the radius from the bolt group centroid to any fastener squared times the cross-sectional area of the bolt. And our terms here are inches to the fourth. Now, if our bolt group is non-symmetric, the radii to each bolt are not equal, we have to actually write this entire term out, which could become quite burdensome in a test scenario. R2 squared A2, so you're going to do a term for each bolt in the group, so on and so forth. And again, our units here are inches to the fourth. Now, most of the problems we're going to encounter are going to be something like this. This would take far too long to do inside of 6 minutes. This is probably where we're going to be going. But we had to understand the theory of how we got here. It is a little confusing after looking at all this to just see, wait, where did all these terms go to? All of a sudden it's nr squared a. It's a little strange, but I think we've covered the theory here. And let's always make sure that we cover our units well. So n is unitless. Radius squared is going to be inches squared. And an area is going to be in inches squared. And I'm going to hammer us on units because no sense missing a problem because we got the units wrong. So, to recap here, this main formula, the first one and the only one we need to know how to solve this problem, is the vector sum of primary shear and secondary shear stress. And just to put it in a pictorial version here, our primary shear is if, let's imagine we've got a rod or a cylinder in single shear, it's got a cross-sectional area, and we've got a force applied to it. And then imagine for the primary or secondary shear, we've got the same rod subjected to a torque. Remember our stress gradient is going to look something like that, with our max value being at R. That's hence the R terms here. So, one thing to notice about this formula, both of these components or terms have an A value in the denominator. And because this is a stress formula, put very simply, stress is force over area. So I wonder if there's a way that we can eliminate some of the clutter here and just go through solving for the force. And that's what we're going to do next, because this is going to take far too long to do in 6 minutes on an exam problem. Okay, so a couple of assumptions here if we're going to use the critical fastener theory. Number one, and this is extremely likely, all the bolts are going to have the same diameter. If they don't, the problem is going to be pretty long and it's going to take a long time to solve, and I don't really think we're going to see that. And number two, the bolt group is symmetric. Now, all the radii might not be the same, but the bolt group's at least going to be symmetric. So this tells us we can use the critical fastener method, which is good. We're going to go through that method, and it's pretty straightforward. So almost all of our examples, our problems are going to have something that looks like this. Maybe not a square or whatever. The shape's not going to be too critical, but it's probably going to be symmetric. There's going to be an off-center load. That's a dead giveaway. But the first step is not quantitative, it's qualitative. We're just going to draw the force vectors, and we're going to find the bolt group centroid. So I've redrawn my bolts here. Primary shear, easy. Split equally. This can be F over 4 for each. Secondary shear, you see we've got force, or our force is going to be turning the joint that way, so we've got a radius. Now I'm not going to put values on these red vectors yet, but just to show you. Okay, now I'm going to redraw this. And we're going to draw these vectors in a more easily identifiable manner. And the reason we're doing this is we're going to find visually the fastener that's experiencing the greatest magnitude of force. And I'm writing the resultant vectors with double arrows just for ease of identification. All right away we can see, I'm just going to label these A, B, C, D. A and D, we can tell already, their force vectors are smaller in magnitude than B and C. And since we know that these vectors are the torsional component, secondary component of these vectors are of equal distance, these guys are the same length, just in different sign direction. Doesn't matter here, we know that either one of these is going to be our critical fastener. We did this step, if we do it multiple times or repeat repetitively, we can do it very quickly and we can quickly identify the critical fastener. Now, if you were to look at, use our cheat sheet, our cheat step and say, oh, which one is the farthest from the bulk group centroid? Well, all of them, but notice that it helps to write the vectors out because it makes it simple. The next step is we're going to compute primary and secondary shear force. And you can see that I've got our generic formula written down here. We're going to end up doing this. Resultant force is equal to F prime plus F double prime. Let's go through each one of these by themselves. We've already covered primary shear stress is V over NA. This becomes primary shear force is equal to V over N, or F over N, if you prefer. And our units here are going to be pounds force. Secondary shear stress, original formula was FERI over NRI squared AI, and we're going to reduce that. F double prime equals F times eccentricity over NR. Shear force times eccentricity, we've covered that. Number of bolts, N. R here is the radius from the critical fastener to the bulk group centroid. R. So again, our units here are pounds force because that's pounds force times inches over inches. Always want to make sure we get our units right. So these terms are far simpler to solve for than the terms we covered just a moment ago. Last step, last couple steps, fairly easy. Okay, we can easily compute what this is, primary vector, and we can easily compute what our secondary vector is. We may have to do some trig, but we can get there. Now, if we're going to vector sum these, this is not a simple vector summation. But what we can do is convert this guy into x and y components. Now we've got a scenario like this. That's just our fastener here. There's our resultant. We can find that. We'll call that FR. We can find that. It's going to be this value here. We're going to sum all of our forces in the x direction, and we're going to square it. And we're going to sum all our forces in the y direction. We're going to square it. Pythagorean theorem. That's easy, guys. We can do that quickly. Then we're going to go the last step, which you may not even have to do on an exam question, but it's good to know it. Our general equation for shear stress is V over A. But to write it for our purposes, resultant shear stress is equal to resultant shear force over the area of the bolt, cross-sectional area of the bolt. Units, pounds force over inches squared. That was so much simpler, guys, than going through some of that ridiculous stuff that we just saw. Remember, when you look in the reference manual, they've got all kinds of junk in there for, they've got summations and they've got R terms that are very confusing. When we go the force route, it's so much simpler. These are easy to find and easy to solve for, and easy to compute stress. A couple notes here. Got to pay attention though. If we're told to compute the resultant shear stress, we need to pay attention to what information we're given about the bolt. If we're given coarse or fine thread and it's standard, we probably have a good assumption here that we should use our minor diameter as D in our cross-sectional area calculation. Minor diameter squared times pi over 4 is equal to our area of the bolt. If it's a metric bolt, as far as I can tell, we don't have any minor diameter info in the reference manual, so I'm probably going to use nominal diameter. Now, when you're solving for cross-sectional area here, it may be that your multiple choice answers will give this away for you. Or you may have to do this, either one of these. You may have to do both of them on an example. But just want to point that out, pay attention. And you have to use judgment here on minor diameter versus nominal diameter. You may not even have to do this step at all. But if you do, just pay attention. Don't go straight to nominal diameter. It may not be right. Guys, that covers it for eccentrically loaded bolted joints. Remember, you don't have to be a genius to pass this exam. Thanks for watching.